1. Determine f prime at 0, where f of x is equal to the floor of negative x squared sine 1 over x if x is not equal to 0, and it's equal to 0 if x is equal to 0. So in order for me to determine this limit, the derivative, I'm going to have to use the limit definition. I don't have any real formulas to calculate this. And so because of that, I'm going to have to use the limit. I'm going to have to use the definition of derivative. And so first off, well, let's see what the floor of negative x squared looks like near 0. So in particular, between -1 and +1. And so negative x squared is between -1 and 0 if x is between ±1. So if x is between ±1, well, obviously x squared is going to be between 0 and 1, and a negative x squared will be between -1 and 0. And so the floor of anything between -1 and 0 is -1. That's the smallest, that's the largest integer. Well, let's see, what is it called? That's the smallest integer greater than or equal to it's the largest, so it's the largest, it's greatest upper, okay, so it's the greatest integer, it's the least integer that's greater than or equal to any of those. And so it's the left one, it's the floor. And so in particular, that says that this is equal to negative, it's -1, so it's a negative sine 1 over x if x is between -1 and 1. Okay, so now let's try to find the derivative at 0. And so the derivative at 0 is the limit. Maybe I'll write it this way. Okay. Is the limit as h approaches 0 of f of h, 0 plus h, let's write it this way, f of 0 plus h minus f of 0 over h. And so this is the limit as h approaches 0 of, well, f of h, for h being small, is, for h between -1 and +1, is going to equal a negative sine of 1 over x. So this is a negative sine 1 over h. And f of 0 is 0. So this is just the limit. This is f prime at 0. Limit as h approaches 0 of, well, negative sine 1 over h. Maybe I'll write it this way. Negative 1 over h times the sine of 1 over h. Okay. Well, you notice here that sine that sine here always oscillates between plus or minus 1. Okay. So in particular, so notice that sine of 1 over h is always between plus or minus 1. Okay, so this is bounded times something that, well, is unbounded. In particular, and this goes to, well, plus or minus infinity. And so, therefore, you have something that's bounded divided by something going to 0. And therefore, I have that this, well, maybe I should say and. H goes to 0. Oh, maybe I should put a minus here. Not that it really matters. And h here goes to 0 as h goes to 0. So you have something bounded divided by something going to 0. Therefore, this derivative does not exist. Neither, and actually none of their one-sided limits exist either. So none of the one-sided limits exist. So in particular, maybe I'll even say that. So in fact, if you look here at the right side, the right sided derivative, well, as h goes to 0, this is going to oscillate between plus or minus 1. And so even if h were greater than 0, this would be going towards, well, a negative infinity, but this is going to oscillate between plus and minus 1. So it's going to oscillate between plus and minus infinity. So this is not going to exist, and neither will the left side derivative. Again, because the sign of 1 over h goes to oscillate between plus or minus and 1. As h goes to 0. So this will oscillate between plus or minus infinity as h gets closer and closer to 0. So this limit's not going to exist. So none of these limits exist. So in particular, certainly the one-sided limits don't exist, so the two-sided limit doesn't exist. Any questions about this? Okay, let me do problem number 2. Find the derivative of the function using the limit definition of the derivative, the definition of the derivative. B, determine the domain of the function. C, determine the domain of its derivative. Okay, so let's do that. So do part A. I need at least 1 or 2 pages here. Let me insert another page. Okay, so let's do this. Okay, so let's find the derivative. Using the limit definition of derivative. It's the limit as h approaches 0. So I'm going to use the difference quotient definition of derivative. And so it's the limit is h approaches 0, there's difference quotients. So f of x plus h minus f of x all divided by h. And so, in particular, it is the limit as h approaches 0. Oh, actually, let me put it there. Of x plus h to the 3/2 minus x to the 3/2 all over h. Okay, so let me try to get rid of the square roots. So let me multiply by its conjugate, the conjugate of the numerator. So let's do that. And so x plus h to the 3/2 plus x to the 3/2 all divided by x plus h to the 3/2 plus x to the 3/2. Okay. And so this is equal to limit as h approaches 0 of, well, this will be the difference of the squares. X plus h cubed minus x cubed over h. X plus h to the 3/2 plus x to the 3/2. And so this is the limit as h approaches 0. So let's use the special product formula. The well, the perfect cube formula or the binomial theorem, x cubed plus 3x squared h plus 3xh squared plus h cubed minus x cubed, all divided by h, x plus h to the 3/2 plus x to the 3/2. So this is equal to x cubes cancel. Limit as h approaches 0. Let's factor out an h. So you have 3x squared plus 3xh plus h squared over h x plus h, oops, to the 3/2 plus x to the 3/2. The h's cancel. So this is equal to limit as h approaches 0, 3x squared plus 3xh plus h squared over x plus h to the 3/2 plus x to the 3/2. So as h goes to 0, well, the 3xh and the h squareds go to 0. The x plus h to the 3/2 goes to x to the 3/2. And so this approaches 3x squared over 2x to the 3/2. And so f prime is just 3/2 x to the negative 1/2. And that's your derivative. Okay. Let's do part B. And I think part B is to find the domain of your original function. So the domain of my original function is, well, you don't want to take the square root of negative numbers. And so the domain of my original function is just that x's cannot be negative. So I want that x here is greater than or equal to 0. The domain of my derivative, okay, come on. The domain of my derivative, well, again, you don't want to take the square root of negative numbers, but you also don't want to take, you also don't want to divide by 0. And so you want x to be greater than 0. Okay. Any questions about this? Okay. Let me do problem number 3. Give a counterexample to the following where only rational numbers are defined. If f is continuous on the closed interval AB, then f is bounded on the closed interval AB. Okay, so let f be a polynomial. A polynomial, well, a rational function. We want a bounded. So that's, actually, let's skip one line. And so let this be 1 over, well, let's say x squared, 2x squared minus 1. Okay, so this is a rational function. And let's do this on, oh, let's say from 0 to 1. Which is the intersection between 0, 1. So on all rational numbers between 0 and 1. Okay. Well, a rational function is continuous everywhere, except where it's not defined. And well, it's, in this case, on the closed interval between 0 and 1 that contains only rational numbers. Well, it's continuous everywhere. And so, so then F is continuous. On the closed interval zero, 1. Because, well, the only place that it's not defined is 1 over the square root of 2. And while 1 over the square root of 2 is not in the in this closed interval that only contains rational numbers, 1 over the square root of 2 is irrational. And so it's continuous on this closed interval. But it's not bounded. As you keep getting closer to, as you keep taking rational numbers closer and closer to 1 over the square root of 2, so just keep taking these rational approximations to 1 over the square root of 2, then this function f keeps getting larger and larger and larger as you keep getting closer and closer and closer to 1 over the square root of 2, taking, of course, only rational numbers. So f of x is unbounded. On this interval. And so we find that continuous functions on closed intervals are no longer bounded. And so that contradicts a lot of the things that we did back in chapter, was it 2, I believe. So a lot of our techniques, our applications of, involving derivatives wasn't valid because of this. Okay. Any questions about that counterexample? Okay, let's do problem number 4. Find the limit or show that it does not exist. Okay, so that's a nice, relatively easy function here. So the limit as x approaches infinity of 3x minus 2 over 2x plus 1. This is the same as the limit as x approaches 0, infinity, of 3 minus 2 over x divided by 2 plus 1 over x. Just dividing every term in the numerator and denominator by x. Well, as x goes infinity, the 2 over x and the 1 over x go to 0. And so I have the numerator approaches 3, the denominator approaches 2. Therefore, this approaches 3/2. So the limit exists, and it's equal to 3/2. Any questions about that? Let me go on to problem 5. Determine the derivative. Y equaling secant x. No, I'm sorry. Determine the derivative, dy dx. Y secant x equals x times tangent y. Okay, so let's do this. And so let's take the derivative of both sides of my equation. And so let's take the derivative of y secant x. And let's take the derivative of x tangent y. And so derivative the first times the second. So secant x times dy dx. Plus the first times the derivative of the second. Derivative of secant x is secant x tangent x. Again, I'm going to use the product rule. And so the derivative of the first, 1 times the second, plus the first, x, times the derivative of the second. Derivative of tangent is secant squared. And so derivative of tangent y is secant squared y times, well, the derivative of what's inside, dy dx. Let's bring all the things involving dy dx to one side of my equation. So secant x minus x secant squared y times dy dx. And let's bring everything else to the right hand side of the equation. And so tangent y minus y secant x tangent x. Okay. And so I just have one little, need just one like additional line to write the answer. Okay, so dy dx. Oh, actually, I wonder if, no, I can't write it. So dy dx is equal to the right-hand side of my equation, tangent y minus y secant x tangent x, all divided by, well, what's in front of the dy dx? Secant. Oh, come on. Secant x minus x secant squared y. And that's your answer. Any questions about that? Okay. If there are no questions about that, then let's do the next problem. Okay, so problem number 6. Determine, oops, Determine the domain of the function. Plot any holes in the graph. Find and plot the intercepts of the graph. Determine the asymptotic behavior as x approaches the x-intercepts. You can omit this step if the equation is difficult to solve for the intercepts. C. Determine the symmetry of the function. Determine if the function is an even or odd function. Determine if the function is periodic. D. Determine the asymptotic behavior of your function at positive infinity, negative infinity, and at any finite value for which the function approaches infinity, and at the zeros of your function, graph the asymptotes using a dashed line. E, there's a lot of parts. E, determine the intervals of increase and of decrease. F, determine the extrema. G, determine the intervals where the function has upward concavity and where it has downward concavity. Determine the points of inflection. H, sketch the graph. F of x is equal to x radical 6 minus x. Okay, good. So let's do this. So A, let's determine the domain of my function. Well, this is a square root. And so to find the domain, I just want whatever inside the square root to be non-negative. And so I want x here to be less than or equal to 6. And so the domain of my function is just negative infinity to positive 6. There are no holes, so I don't have to worry about that. Find and plot the intercepts. Okay, so intercepts. Well, I certainly need more. Okay. So let's find the intercepts for my function. Well, let's find the y-intercept. And so my y-intercept is just 0. So my y-intercept is at the origin. And well, as x goes to 0, this actually, the asymptotic behavior is very close to, well, so f of x here is, well, as x approaches 0, radical 6 minus x goes to radical 6. So this is very close to radical 6x as x approaches 0. Oh, and the x-intercepts. And so I have here that when is f of x equal to 0, so x, rad x minus 6, rad 6 minus x. Well, this is 0 when x is 0, or when 6 minus x, x is 6. So when 6 minus x is 0. Okay, so I have x-intercepts at the origin and at 6, 0. Well, I've already looked at the asymptotic behavior as x approaches 0. So it's that. And let's look at the asymptotic behavior as x approaches 6. And so as x approaches 6, well, x approaches 6, so it's very close to 6. And radical 6 minus x is, well, radical 6 minus x as x approaches 6. Okay. Okay. Problem the ABC, C. So part C. Determine the symmetry of the function. There is no symmetry. So symmetry. And so let's look at f of negative x is equal to negative x radical 6 minus the negative x. And this is neither equal to f of x nor minus f of x. So it's neither even nor is it odd. So not even, it's not odd. Okay. And well, it's certainly not periodic. There does not exist a t such that f of x plus t, well, a non-zero. Obviously, if we plug in 0, a non-zero t such that f of x plus t equals f of x. Okay. And so it's not periodic. So it's not, there's no symmetry. So I have no symmetry here at all. Let's do, that was C. Yeah, so C gave us nothing. Let's do D. Okay, so part D, determine the asymptotic behavior. Okay, so, well, as x goes to infinity, it just goes to infinity. There's no real asymptotic behavior, nothing that it goes, well, I guess as x goes to infinity, this doesn't exist. Well, no asymptotic behavior as x goes to positive infinity because that's not in the domain. And so maybe I'll just say that. No asymptotic behavior as x approaches positive infinity for obvious reasons. My function is not defined past 6. And so it certainly has no behavior. Once you get past 6, it's not defined. So let's go to negative infinity. So as x goes to negative infinity, well, it looks like x to the 3/2. So you can disregard the 6 here. So you can disregard the 6 here. And so it looks like x times the square root of negative x. And so that's, well, an x to 3/2, so a negative x to 3/2 as x approaches negative infinity. So if x goes to negative infinity, it looks like an x to 3/2, a negative x to 3/2, a negative x to 3/2 power. Okay. And your function doesn't go off to infinity for any finite values. And we've already seen that as x approaches 0, it looks like x radical 6. And we've also seen that it looks like 6 radical 6 minus x as x approaches 6. Okay, so we've seen those. Okay, so that's all of its asymptotic behavior. Now let's, take derivatives. So now for part E, I want to find the intervals of increase and decrease. So let me first find the derivatives. So I can use those on the next two parts of this, or next 3 parts actually. And so f of x is equal to x times 6 minus x to the 1/2. Let's take the first derivative. So I'm gonna have to use the product rule. So the derivative of the first times the second plus the first times the derivative of the second. And so bring down the 1/2 on front, rewrite what's inside, all to the exponent of 1 less, all times the derivative of what's inside. Okay, so this is equal to let's just simplify it slightly. I want to take the second derivative. So this is 6 minus x to the 1/2 minus, well, this is going to be minus 1/2 x times 6 minus x to negative 1/2. Okay, so this is equal to, let's multiply, let's get a common denominator. So the common denominator is 2 over rad 6 minus x. Let's multiply and divide by 2 rad 6 minus x. So that becomes a 2 times 6 minus x. The 2's cancel, so you just get an x, and everything else cancels. Okay, so this is equal to 12 minus 2x minus another x is minus 3x over 2 rad 6 minus x. Factor out of 3, 4 minus x over 2 rad 6 minus x. Okay, good. So that's the first derivative simplified as much as possible. I don't know which one is easier to take the derivative of. Maybe defining the second derivative. Maybe I'll use this. So maybe I'll use this form here. And so otherwise you have to use the quotient rule. I'm not sure if I want to use the quotient rule yet. And so the second derivative is, okay, so I'll bring down the 1/2 out in front. Rewrite what's inside to the power of 1 less times the derivative of what's inside. Minus, here I'm going to have to use the product rule. And so minus 1/2 times 6 minus x to the minus 1/2. Okay. Okay, so that's the derivative of the first times the second plus the first. Maybe I'll say minus, so x over 2 times the derivative of the second. And so the first times the derivative of the second, so I'll have to bring down a negative 1/2. Rewrite what's inside the parentheses to the power of 1 less times the derivative of what's inside. So this is equal to negative 1/2. 6 minus x to the negative 1/2. There are minus 1/2. Oh, there's another minus 1/2. So you have a minus 1/2 minus a 1/2 gives you just minus one of these. And so this is, since I have two of these, I have a minus 6 minus x to negative 1/2. Since these two are the same, then there's 1, 2, 3 negatives. So that's a minus, and a half times a half is a fourth. So it's minus x over 4. 6 minus x to negative 3/2. Okay. And so the second derivative well, I have to find common denominator. So common denominator is x times 6 minus x to the 3/2. Okay, so that's my common denominator. Well, maybe I'll write it up here. So 4 times 6 minus x to the 3/2. And so I'll multiply and divide this first term by 4 times 6 minus x. And well, the only thing remaining in the for this part is just x. And so my second derivative is negative 24x, negative 24 plus 4x minus x is plus 3x over 4, 6 minus x to the 3/2. So the second derivative is a factor out of 3. What remains is x minus 8 in the numerator, and then a 4 radical 6 minus x cubed. Okay, good. Let's determine the intervals of increase and decrease. So to do that, I'm going to have to determine my critical numbers. Okay, so let's find the critical numbers. So I want to, that's why I simplified this guy. I can hold it. Okay, so that's my first derivative. So I want to find where the first derivative is 0. And where the first derivative does not exist. Okay. And so I set the numerator equal to 0. So x is equal to 4. I set the denominator to 0. And solve for x. Okay, this actually occurs at one of the endpoints of your domain, in the domain. And so I have here that x is equal to 6, which is an endpoint. So let's try to determine. Oh, come on. Where this function is increasing and decreasing. Actually, let me grab the derivative. Oh, if I can. Here it is. So let me grab this so I can see the signs. Okay, so let me scroll if I can. Okay, good. Okay, come on. Ah, 90% of my time is just spent fighting with this computer. It will not do what I want. It will not write what I want. It will not erase what I want. Okay, still just trying to erase because it did not write what I wanted. Still trying to erase one line. Okay, let me write the derivative down. Hopefully I can erase it once it gets on here. Okay, so hopefully it's going to, oh, it did appear what I should do. Okay, so 4 and 6. Okay, come on. And over here, my function is not defined. So this is not in the domain. Okay. So let's try to determine the sign. The sign of the first derivative. Okay, so you take a number less than 4, let's say 0, positive, positive. So it's increasing. Take a number between 4 and 6, let's say 5. Negative over positive is negative, so it's decreasing. Okay. And so this is a local maximum. Okay. And this is an endpoint extrema. Endpoint minimum. Okay. I'm just trying to write minimum there, endpoint minimum. Okay, so let's write the intervals and increase. Negative infinity to positive 4. Interval of decrease. from 4 to 6. Okay, good. So those are intervals of increase and decrease. Well, determine the extrema. Oh, we already have. So let's see what happens at 4. So f at 4 is 4 radical 6 minus 4. So that's 4 rad 2. And f at 6 is 6 rad 6 minus 6. 0. So we have a maximum at 4 rad 2. And we have an endpoint minimum. So it's not really a minimum, it's just the fact that it ended there, the minimum, because obviously you can't go any further. So it's a endpoint, it's not a real minimum, it's an endpoint minimum at the origin. Okay. G. Let's try to find the intervals of concavity. So let's try to determine the possible points of inflection. Okay. And so let's look at the second derivative. Find where the second derivative is 0, or where the second derivative does not exist. In the domain, of course. And so set the numerator equal to 0. So x is equal to 8. Set the denominator equal to 0. Oops. So x is equal to 6. Again, this is an endpoint. And so it's not really going to be a point of inflection. Well, it can't be because it's at an endpoint. So let's try to find, well, good, it's drawing it. Okay, let's look at, oh, this is also not in the domain. So that's not in the domain. So if I look here, I'll just put down the number 6. All this over here is not in the domain. Okay, so let's sine of the second derivative. Let's plug in 0, so negative over positive is negative. So it's concave down. So it turns out that this function is always concave downward. Okay. Next. So the intervals of concavity. Well, they're boring because it's so intervals of concavity. You had at least 2 more pages here. Okay, so in this case, 6 minus 6. So the interval concave downward is well the same basically as the domain. Negative infinity. Oh, come on. Negative infinity to 6. Okay. Let me do, so that's H. So I guess H, we're at H now. So H is just a schizograph. So we should have everything that we need to schizograph. So let's see. Six. So it went through the 6. So those are the intercepts. And well, it looks like, so this is the graph of y equaling x rad 6 minus x. Oh, so this maximum's at 4. And it's 4 rad 2, which is what? 4 red 2. 3, 4, 5. Out here. Okay, so it's somewhere around there ish. Okay, so it's asymptotic to, let's do it this way. So near x equals 6, it's asymptotic to 6. We had 6 minus x. So it looks like sort of a square root function near here. And it's almost linear here. So as x goes to 6. As x goes to 0, it was f of y is asymptotic to, let's say, x rad 6. Okay, so it looks linear. So it flattens out here. Okay, so it's, and it's always concave down. Maximum, then just there. Yeah. Let's make it nicer. Okay, good enough. Okay, so it's a little wobbly here, but that's more or less what it looks like. So I have a maximum here of 4. 1, 2, 3, 4, 5. Good. It's a little bit of, should be bigger than that, but I'm having a little bit. Oh, come on. Okay, so 4 rad 2 is your maximum. And of course, in this case, it's a global maximum because it's always concave down. So it looks something like this. My steepness here is a little high, but that's a little steeper than it should be. But, oh, actually, wait. Actually, I think it does go infinite there. Okay, so problem number. So 6 was long. All the rest of them were pretty fast. 7, okay. So let me do problem number 7. Use differentials to approximate 1.999 to the power. Okay, so let's do that. So why aren't you working? Okay, come on. I'm just trying to write. Okay, so let f of x equal x to the 4. And maybe I'll use this notation. I'll let a equal 2 and delta x, just do up delta x, equal negative 0.001. Okay, so f prime of x is 4x cubed at 2. It's equal to 32. And so I have that dy is equal to, well, f prime, say at a, dx. And so this is equal to 32 times negative 0.001. And so I have that this is equal to a negative 0.032. Mm-hmm. To another page here. F at 2 is equal to 2 to the 4th, 16. So delta y is approximately equal to dy. So therefore, f at a plus delta x minus f of a is approximately dy. And so 1.999 to the power 4 minus 16 is approximately negative 0.032. And so 1.999 to the power 4. Well, adding 16 to both sides of your equation, you get 15.968. Okay, so that's your approximate answer using differentials. Okay, good. Let me do, oh, good. Let me do problem number 8. Actually, I don't need that there. So let me do problem number 8. Let a sub 1, comma, a sub 2, comma, a sub 3, dot, 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 comma, a sub n be real numbers, not all 0. Prove that the equation radical 1 plus x plus radical 1 plus a2, a3x plus dot, 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 plus radical 1 plus a sub n x equaling n has at most one non-zero real root. Okay. So let's try to prove this by contradiction. So first off, let f of x equal all of these. Maybe I'll write it this way. The sum I1 of x to the 1/2 minus f. Okay. So let me so f prime 1/2 times, well, so negative 1/2, all times the derivative of what's inside, which is a sub I. Let's look at the second derivative. Oh, and of course, derivative of a constant is 0. N is just a constant. Same n as this, of course. So this is going to be the sum, I equal 1 to n of, bring down the negative 1/2 again, so that's be a negative 1/4 ai times 1 plus aix to the power of 1 less, negative 3/2, all times a sub I. So that's a sub I squared. Now, the domain, well, let's see. So one of the things to notice here, you're adding up, well, this is the a sub I squares have to all be less than or equal to the a sub I squares. Of course, a sub i's are real numbers. The a sub i's are real numbers. Therefore, their squares always going to be greater than or equal to 0. And so all of these here are going to be non-positive. Multiplying this, which is going to be, again, well, non-negative. And so this whole thing has got to be less than or equal to 0 for all x in the domain. Of your function. Okay, so actually, maybe I'll say what the domain of the function is. Not that it really matters. Figure out the domain of the function. So it really doesn't matter what the domain of the function is, but okay, so if I look at these, well, I don't want to take the square root of negative numbers. Okay. So I want that these, I want to be equal to 0. Okay. So let's see when it's equal to 0. So I want each of these a 1 plus ai x's. I don't want any of these to be less than 0. Otherwise, I'll be taking the square root of a negative number. Okay, so let's figure out when it's equal to 0. Oh, come on. So x is equal to negative 1 over a sub I. So I want to, so I, in this case, has to be, well, let's look at the, oh, when the a sub i's, let's say, are positive, in which case I want the smallest of these. So that's going to be the largest of the a sub i's. So this is equal to, so the domain, oh, and it depends on what if all the a sub i's, so let m, let's say, equal the maximum for I going from 1 to n of the set of a sub I to n plus. Okay, set is greater than is greater than 0. Let me do another page so I can write this down. And let m minus that'll give me also the smallest. I want the maximum from 1 to n of the absolute value of a sub I if a sub I is less than 0. Okay. Oh, and let's see. So let, what I'll call it, maybe I'll call it m plus. Let this equal the maximum. Well, no, let it equal 1 over m plus. If, well, m plus exists. If there exists an I such that a sub I is greater than 0. It's equal to infinity otherwise. And let's keep the sign with it. So it's a minus that. No, I'll keep it like this. And then I'll change the sign down here. And so let m sub I m minus, oh, come on. Equal negative 1 over m minus if there exists an I such that a sub I is less than 0. And it's equal to negative infinity otherwise. So in the default case. Then the domain of f is just m minus to m plus. Oh, actually, it's the compactification of that. How do I say that? So it's actually equal to this. It's a closed interval, but of course, if this is infinity, then you don't include it. So if either of those are infinity, you don't include the endpoints. So how do I say that? And you don't include the endpoint. So don't include the infinity. Meaning, obviously, you can't include infinity as one of the endpoints. I don't know how easy it is to say that, but I don't know. Okay, so, but at least this is not, but the derivative, the domain of the derivative, at least, I can say that. The domain of the derivative is the open interval. So I don't need to dance around what happens when it's plus or minus infinity. Okay, good. So it's as small as it possibly can be. Okay. So now, let's try to, so note the following, that of course, f at 0 is 0. Because if you just plug in 0 here, well, you get 1 plus 1 plus 1 plus 1, up n times is equal to n. So if you look at this, you're adding up 1 n times, subtract n from it, so you get 0. And so f at 0 is 0. So now this function is always concave down. So the question is, if the function is always concave down and it has a derivative that's 0 at 0, how in the world can it have another root? Can it have more than one root? Okay, so you only have one root. And so let's do that. This is very dependent on the fact that it's real numbers. So suppose, so now that I've gotten all this set up for you, let's suppose that x1, x2, x3 are in the domain of my function, and that f of x1, oh, and let's suppose, let's make some ordering on it. Let's suppose that x1 is less than x2 is less than x3. And let's suppose that f of x1 is 0, f of x2 is 0, and lastly, f of x3 is 0. So suppose on that. Okay. So now, well, I'm going to try to derive a contradiction from this. The first derivative, so f is continuous on the closed interval x1 to x2, f of x1 is equal to 0, f of x2 is equal to 0, and f is differentiable on the open interval x1, x2. Therefore, by Rolle's theorem, there exists some, I don't know, let's call it y1 in the open interval x1 to x2, such that f prime at y1 is equal to 0. Okay, so I have some, if I'm 0 somewhere, then somewhere in between, I have a derivative that's 0. Okay. Next, as long as my function is continuous on the closed interval and differentiable everywhere in the open interval. So I'm almost done. So now we have the same thing. So do the same thing for now for x2, x3. Of course, probably one of these is 0 because we know that f is 0, 0. So f is continuous on the closed interval x2 to x3. F is differentiable on the open interval x1 to x2. And f is 0. X2, x3, sorry. I'm talking about 2 and 3, sorry. And f is differentiable on the open interval x2 to x3. Now, of course, this is because x2 and x3 are in the domain of f. And so it's also, except at the endpoints, it's also on the domain of the derivative. And so it's the open interval, therefore it's differentiable everywhere in the open interval. So f of x2 is 0 and f of x3 is 0. So by Bool's theorem, we have that there exists a y2 in the open interval x2 to x3 such that the derivative at y2 is equal to 0. Well, since y1 is in the interval from x1 to x2, open interval from x1 to x2, and y2 is in the open interval from x2 to x3, then y1 is less than y2. We have that the first derivative, the second derivative, but the second derivative of f is less than or equal to 0 for all x. So that says that the first derivative, well, so the first derivative here is non-increasing. But f prime at y1 is 0. Well, maybe I'll just say this. That f prime at y1 is the same as f prime at y2. You have something that's getting smaller and smaller, but it's equal to the same thing at 2 points for y1 being less than y2. Well, the only way that this can occur is that if this function here is constant. So that says that f must be constant. So f is constant on the interval x1 to x3. But if f is constant, well, the only way that this function here can be, that f prime is constant, the only way that this can be a constant function is if each of the a sub i's are 0. And so that implies that all the a sub i's are 0. But that's a contradiction. Our supposition was that they're not all 0. So I've assumed that there were 3 roots. So there can be those 2 roots. One of them is 0, because I know f of 0 is 0. So they're at most 1 non-zero root. And that's what you wanted to show. Basically, if you look at this function here goes to the origin. So it could look like this. It's always concave down, or it could look like whatever. It's always going down. So it could look like this. It could look like this, or like this. But it's always concave down. So you have maybe 1 root, maybe 2 roots, but certainly have 3. You're always going down. So there it is. Okay. It's really, okay. I added some little things to make it seem a little fancier to find its domain in that, but I guess that was not really necessary. Just being extremely complete, maybe overly complete. Okay, so let me do problem number 9. Okay, so problem number 9. Oh, got 3 minutes. I went overboard on proving that problem. Problem number 9. If x squared plus y squared plus z squared equals 9, dx dt equals 5, dy dt equal 4, find dz dt where x, y, z is 2, 2, 1. Okay, so let's do that. So I have x squared plus, okay. Come on. plus y squared plus z squared is equal to 9. So let's take the derivative of both sides of my equation with respect to t. Okay, so I have 2x dx dt plus 2y dy dt plus 2z dz dt equals 0. And so I can divide everything by 2. And make my life slightly easier, slightly smaller numbers. Okay, so add one more page here. Plug in x is 2, dy dx dt is 5, y is 2, dy dt is 4, z is 1, dz dt. And so 10, 18. So dz dt is equal to negative 18. And that's your answer. Okay. Oh, problem 10 we could do in like 2 minutes, but we're done with time. So I guess we'll do this tomorrow. Any questions about anything? If not, then that's it for today. And I'll see you guys tomorrow. Okay, then. Happy now. So let's do problem number 10. Find the dimensions of a rectangle with perimeter 100 meters. So let's call this X and Y. And so it has a perimeter of 100 meters. Whose area is as large as possible. Well, the area of a rectangle is length times width, x times y. The perimeter of this rectangle, in this case, adding up all the sides, is 2x plus 2y. And so from here, I get that x plus y is 50. Let's solve for y. And so y is equal to 50 minus x. Therefore, the area A that I want to maximize is just x times 50 minus x. And so this is equal to 50x minus x squared. And so let's take the first and second derivatives. Let's try to maximize this. Since it's a polynomial, it's easiest to use the second derivative test. So this is 50 minus 2x, and the second derivative is -2. So it's always concave down. And so I have that. Let's determine the critical numbers. So I have the 50 minus 2x. Well, I want to find where the first derivative is 0. Or where the first derivative doesn't exist. Well, it's a polynomial, so this doesn't give us anything. So the first derivative is 50 minus 2x. Solve for x. And so x is equal to 25. Let's do the second derivative test. And so the second derivative, 25, is -2, which is less than 0. So it's therefore, this is a maximum. But since the second derivative is always negative, since it's always concave down, then this is a global maximum. There's only one maximum. This is a global maximum. Just like what we saw yesterday when we did, I think it was what, problem 7 or something on this exam, where we used Rolle's theorem to show that you can only have really one extrema if it's always concave down. If it's always has, well, if the concavity is always negative, is always down. Okay, so I want to find the dimensions. Okay. Well, let's determine y. Y is 50 minus x. Therefore, we have a global maximum. So the area is maximal for the square, the rectangle, with dimensions 25, I believe, meters by 25 meters. Okay.